Okay, thanks everyone for coming. I know today we have planned for presentation of a single paper that is most recent deep learning cluster scheduler paper in, what is it, OSDI 2020. But for the purpose, since this paper is very different from the previous papers that we read or look at in this reading group, so I actually put together several paper slides so we can go over the brief history of GPU cluster schedulers work and to see how each new paper attacks the previous paper about what is the shortcoming or challenges that the previous solution does not resolve, or what is their problem. And the deep learning cluster or GPU cluster scheduler is actually a relatively new research area. I think the first paper comes out of Microsoft is in OSDI 2018. And after that, every year you could see one or two GPU scheduler paper appears in the top conferences. But it is actually on a very old topic of the scheduler optimization, how to utilize the resource, because those topic has been explored in HPC area for a long time. But given the different nature or characteristic of the deep learning work and the resource, particularly GPU, then the previous or existing scheduler basically cannot be directly applied to the new clusters. So we can let's look at the what it means to have a scheduler at the GPU cluster. Here you would have a cluster that have multiple machines. Each machine will be attached to, in this example, 4 GPU device. And you start with a single cluster with static layout or static physical resources. And then you have users that share in the entire GPU cluster. And then each user submits jobs that can be simplified as describing, here is the deep learning training job, and I need this number of GPUs for my job. So you have 2 GPU, 4 GPU, 1, 2, this GPU tasks. When this job description comes to the scheduler, the way we say scheduler, it actually contains 2 major components. The first component, scheduler, had to make a decision that when I receive a job, do I immediately deploy it to my cluster, or do I make it wait in the queue, or do I actually go to the cluster, suspend a running job to release the resource required for the new job, and then so I can deploy the new job first. So the scheduler manages the execution time of each job. Once the scheduler has decided the job, like for example, this job 1 should be executed first, should be deployed first, it sends this job to a placement manager or placement plan generator who look at the job's resource requirement and decide where do I actually place this job into my physical location. And by the way, if you have any questions during the talk, feel free to just ask. So here we see that job 1 GPU eventually is mapped to this single GPU in a node that is free. So there are, in this slide, it shows that the purpose of these 2 components, the goal is to minimize the whole cluster-wide average job completion time, GCT. But keep in mind that this is only one of the objectives. So usually depends on the requirements of the team or of the company, you could have different objectives. So average job completion time is good, but is sometimes will lead to some starvation of some teams, like large jobs, because the large jobs require more resources, so they stay in the queue longer. And so there are other objectives like fairness. So which basically is saying that if I have my own cluster of this many GPUs, my job, according to my quota, my job would have been completed by now. But since I have shared this cluster with many other users, and even though the shared cluster is 10 times more than my original resource with 10 users, but my job still starve because of the scheduler. So the fairness, this GCT does not guarantee such fairness, and there are other algorithms or papers that actually make that as a goal, as an objective, and then try to optimize that. And also the GPU resource utilization is another main factor or main goal. We don't want any single GPU to be idle for too long. That will be waste of resource and waste of money. So challenge number one: unpredictable training times. So when a deep learning training job is submitted, it's basically some Python scripts that is calling the standard framework, TensorFlow or PyTorch, that's executing the training job. But the model differs from each other, and each training job is basically very different from another training job. Sometimes people make mistakes in the training scripts, so the job actually takes a lot of resource, or it runs longer without convergence. So it's basically unpredictable. So that's one of the challenges for the scheduler. The second challenge is the job consolidation. So if you put the job into map to the physical machines too sparse, that would mean that for a job for distributed training job that requires multiple GPUs and multiple workers on the GPUs, they exchange message, or they exchange the learned parameter for each training iteration in a very large volume, and it puts a lot of load on the network in between the machines. And if that placement actually harms the performance of the training job, and also delays the execution time. So for example, in this case, even though the job with 4 GPU requirement comes into the queue and we have 4 available GPUs, but they spread across multiple machines, and if we directly place this job into this GPUs, it not only affects this single job, it also affects the running jobs, that if they have any communication between the workers. So the better way maybe is wait for one of the job to finish to free up all 4 GPUs in one machine, or suspend that job to free up this, depends on the priority, and then you place the whole job into the single machine. But that also means you have a longer queuing delay, right? So even though this you have optimal performance on a single machine, but your job has to be wait for that resource to be available, and you also create the fragmented free GPUs in the cluster. For example, this 3 GPUs then cannot satisfy the second job, and you don't have anything to be run in the single laying around GPUs. So this is one of the paper that in 2019, it basically compared itself with the previous work, Gavel, which is almost the first GPU cluster scheduler paper that appears in OSDI 2018. And what it's comparing with is basically saying that the traditional scheduler that does not, either not considering how to attack the unpredictable training time, because since once you have decided the job can be scheduled, then you cannot change that decision. That job will run in the cluster until it finishes. Or you have the FIFO, basically the first job first in, and that will be first coming out for schedule. And for job placement, there's basically non-decisions making. They are randomly placed or placed in a round-robin order, that without even considering this GPUs are closer together or far away from together, or how do you utilize them. So Gavel is the almost first paper to discuss this. in the context of the deep learning. And what it does is basically use a profiling, so and use a profiling and the time sharing mechanism to schedule the jobs. So it compares itself with the traditional scheduler because that's almost the first paper to do this. And it says compared to this, what Gavel is able to do is I can continuously recover from my previous schedule mistakes or optimize during the runtime because it has the ability to suspend the running training job and then replace with the new jobs. And what the traditional scheduler do with the profiling is when you schedule a job and then you profile the CPU and GPU utilization of the system, of the hardware, and then look at that and compare if two jobs, how do they utilize, and then you decide, oh, if one of the jobs is actually utilizing the CPU very low, I can place another job on top of it. So I can co-locate two tasks, whether it is a HPC task or a normal CPU task. I can co-locate them together so they can utilize the resource better. But for GPU, actually you cannot, the Gavel argues that you cannot directly use that hardware profiling because it also includes the overhead of the resource during the training. So you should actually, because you know the framework, you know the deep learning module, so it's actually better to calculate the mini batches, the throughput, so the mini batches per second. And this throughput of the training job is actually the useful work it is actually doing. So in order to actually achieve this scheduler, so Gavel introduces that we need the clients actually running alongside, co-located with the training job in the container, in the cluster to perform the starting of a job, the pause or resume of the training jobs, those kind of things. And it also requires some modification of the TensorFlow and PyTorch, the popular framework, to do the time slicing or migration. So if you imagine that if you have a training job running in one node on one GPU, and scheduler decided this job should be suspended for now and resume later in another device, then it requires the framework to actually take a snapshot of the entire GPU memory and then load those GPU memory into the main memory and then send it over to another location to resume from there. So it actually requires a lot of working to achieve that suspend and resume. But once you have that, then you can enable the time slicing for scheduling. Basically, for each slice of time, it look at which job should be deployed during this time and which job should keep running in this time, which job should be suspended, and so on. And then there's packing. So what Gavel is trying to do is when it deploys the job during training, for example, in two different machines on two different GPUs, and during runtime on the fly, the client side co-located with the training container can actually collect the data, collect the metric of what is the GPU utilization on that machine. If the utilization is actually very low, which means this two job does not require much of GPU computation or much of RAM, then I can co-locate these two jobs together on a single GPU. And that will help to achieve a higher throughput. So here you can see that when this long running job and short running job started with different number of GPUs, some of the jobs scheduled first, they achieve very high throughput. And then Gavel comes in after some time, after runtime, and saying that, hey, we should enable time slicing. So it slices the time to give fairness for each job to complete at a lower throughput, but every job gets to run. So nobody starve for the resource. And finally, some of the short job finishes, and then the throughput goes up the job for individual jobs throughput goes up again, but your net throughput is keeping at the same level. And the second for packing the placement is they did experiment with two jobs, and then the first job is running, and then for next time slide, the second job is running, the first job is basically suspended, and then it resumes, the second job stop after several rounds of interchanging. What the actual observation of the client side is, the GPU core utilization is very low. So you have 3,000. What is this? Is memory? Okay, you have the one is 100% cores utilized. If the utilization is actually less than 50%, then you basically can place those two jobs together into the single GPU, and they will both achieve what they are required, but your throughput is now very high. So that's the Gavel paper. And then next year, the new paper comes up and saying that it's good, but there are other aspects of this scheduler thing. Is what if I do not have the complete job information? How do I, without this time slicing, how do I achieve a better schedule? Better scheduler at the time. So the first challenge is I don't have a complete information of the job. So what can we know about? The first characteristic it's observed is if you look at all the training jobs in an existing cluster, it's just real training jobs. Even though most of the training jobs has only running on single GPU and finishes within 10 minutes, but you still have a large number of other type of jobs that's finish with a longer time and utilize 2, 4, 8, 16, 32, or even 128 GPUs. That's what they require. So when you look at the scheduling of a job, by simply looking at job execution time is not enough, because different job may use different GPU numbers, and then they achieve different execution time. So scheduler should be considered both the temporal aspect and the spatial aspect of the training jobs. A good way to visualize that temporal and spatial aspect is to use this coordinates. We have the time axis here for whatever unit time it is. And then we have the number of GPUs on y-axis. And then the first job that executed for 5 unit time and that uses for 2 GPUs will basically represented by this rectangle, the area of this rectangle. And what this paper utilized, given this spatial aspect of the training job, is actually a very old scheduling technique. The first is coming from a 1968 paper called Least Attended Service, LAS. The least attended service is basically I will calculate the executed time, which is the number of GPUs multiplied by the execution time so far. And then that would be my executed time. And whichever job has the least of the executed time, it should have a higher priority to be scheduled onto the scheduler. So by that execution, the goal is to minimize the average job execution time. And if this is LAS is for completely unknown job completion time. So if a job comes in, I don't know how much actual time it requires for this job to be complete. I can just use the LAS on the runtime that as it's deployed, executed, and then I can recalculate this executed time every time when needed, and then decide should it be suspended or should it continue to execute. But they also argue for the well-known models, like in production, you have a lot of image models or natural language processing models that's already been used by many production pipelines that you have a roughly idea that's how much time this job should actually finish for training. Then you could use something even better, but still, this is an old technique from 1989 called Gittins index policy to calculate this scheduling priority. So when a job comes in, you calculate the total execution time, and then if you don't know anything about the job, you just use this LAS. If you know, you use the index. Here's an example. So job 1, 2, 3 have different requirements of the GPU 2, 1, 2, and the execution time is 2, 8, 6. So the distribution of the execution time is multiply these two numbers together. So you have 4, 8, 12. And then at the beginning, no job is deployed, so attended service is all 0. But if you use the Gittins index, they have the same index at first. So you decided to deploy the job J1 first. So you have a little square here with 2 GPU with 2 execution time. And then let's assume your cluster only have 2 GPUs. So you can only schedule 1 job at a time because they require two jobs. So when you deploy the job 2, which even though only use 1 GPU, you cannot deploy job 3 because it requires 2 of them. Now, after this unit time 6, it decided job should be switched, even though the job 1 did not finish. It should be switched to J3 because the index is higher. Okay, when it switched to job 3, but job 3 requires 12 or 2 GPU with 6 unit time, so it's clearly not finished within 2 unit time. Then it switched back to the G1, G2, deployed for some time, and then G2 actually completed at 12. And then it prioritized, and then scheduled the last job, and it ended with unit time 60. So by this way, wait, there should be another slide. So basically, if you use the Gittins index, the average job completion time is only 10, but if you use the least attended service, the average completion time in this case is 11.7 or something. So it gives you, once you know more about the job completion time, then you can do more to optimize the schedule. So the LAS and Gittins index solve the first scheduler part, but oh yeah, 11.7 here. So if you don't have extra information, then average job completion time based on the least attended service is 11.7 is higher than the Gittins index. So this is for the training time for the scheduler part. But what about the placement part? How do I decide this job? How should the job be placed onto the physical cluster? What this paper is given is actually a very simple solution. It's not complicated. But it will be attacked by later papers in this aspect. What is saying that we can observe for the well-known training models, VGG or AlexNet or ResNet, we can see that the size, the number of tensors or the parameters that they have or they exchange between the GPU workers is very different. So the VGG net have a large number of parameters, and the parameter size is larger for worker to exchange. So it's better to put this workers for this kind of neural network closer together because they utilize a lot of bandwidth. And for this other type of a job, which the size of the parameter is not that large, you can actually deploy them far away and utilize more singleton GPUs that's not located in the same machine. And basically they give the simple solution saying that the scheduler will have a model profiler and decide, am I going to collocate them, or am I going to, or I don't care. If I need to collocate them, then this job will be waiting on the resources, waiting on the GPU that's on a single machine. whereas these jobs can be immediately deployed regardless of where the GPU is. So a later paper, this is another paper called Themis, I think. So in that slice, it attacks the TRAS's LAS scheduler mechanism as the metric is, like we said, the attended service, LAS, and it allocates for the least duration to minimize this attended service, but it doesn't, but the placement preference is really bad. So basically the same argument, the VGG module prefers the dense placement because they exchange the parameters in a large volume. And what that paper is trying to achieve is actually the fairness that different teams sharing the same cluster is trying to achieve. That they use an auction model that's saying that for every job that's waiting for the deploy, you have to, and there are some resources available, and then each job will report their own performance, their own raw throughput from the container itself. And then based on their throughput and their requirements for placement, then every job will, made a bid on the scheduler, and scheduler pick the next, the best bid, and then trying to place them. So I won't cover that in this talk. But finally, we kind of, from this slide, we kind of get the idea that what challenges or what problem we face when we're trying to make a scheduler for the GPU cluster. And so far, what we have been saying is they assume a cluster, but they don't know what the cluster looks like. What is the actual hardware running in the cluster? They assume that when I deploy a job into the cluster, they whether it is running in machine 1 or machine 2, they're running roughly at the same throughput. The only concern is the network bandwidth between them, the network contention between the workers that communicate, and that affects how I place the jobs. But if the jobs are individually isolated and each job is running on its own machine, then I would assume that the same job running on machine 1 and machine 2 has the same speed, has the same throughput. And the goal is minimize that average time execution time, or the fairness that becomes a single value. So the priority becomes a single value. And the latest work that we're actually going to look at today, the Heterogeneity-Aware cluster scheduling policy, is arguing that this is actually true. In today's cloud provider, if you have a GPU cluster, because the training devices, the GPU cluster, the GPU, physical GPU, it renews very often. It renews every year. We see new generation of the GPUs or new generation of the accelerator to be deployed in the cluster, but you don't want to lose the old GPUs immediately, right? So it comes with a cost. So you would have a cluster that have mix of devices, and they all have different performance, different throughput, and the scheduler should make that into the consideration when you deploying the job. So when a job comes in, even though they're writing in the same framework, the PyTorch and TensorFlow, deploying this job into a different device will end up in a different throughput. And also, it also argues that since we have different objectives, how can I satisfy all of them? How can single scheduler to satisfy the different teams' objective when you're scheduling the jobs for the entire company or all the different tenants? Here is the comparison that of the performance that they did. Basically, if you look at the some module like transformer, when you change the GPU type from K80 to P100 or V100, it only has 3 times improvement of the throughput. But other NAT modules, like ResNAT 15, it can go up to 9 times throughput increment. So a different module running on different hardware also could end up in different improvement of the throughput. So you actually have to consider all of them. And this for multi-objectiveness, like when the product team and research team share the same cluster, maybe the research team's priority is to FIFO. Each newly submitted job should be scheduled first. But for production, we need the fairness between the job because production cannot allow any jobs to be starved for too long time. But if you want to share the same schedule between these two teams, then you have to, make 2 objectives instead of a single objective optimization. And this paper lists the previous papers that we have looked at. The Gandiva, the first one, and then the same is the attack in the Gandiva and attack in this terraces, and the terraces is the one that we look at using the least attended service time. And all of this is only considering the cluster with the same resources. But there are some other works that we didn't look at. Actually compare the performance with different GPU types, but they have a single goal. So they either have the maximum mean fairness as their objective to optimize for, or the GCT, the job completion time, as their objective to optimize. And this work is trying to combine all this together, and they do it in following way. So there are scheduling policies with different objectives in mind. So FIFO, shortest job first. So this basically shortest job first policy is basically trying to optimize the resource utilization, because you would, every time a small jobs comes in, you will deploy that first, so you don't have any GPUs lying around that's basically running idle. And then you have the minimum cost, that if this is a cloud service, that different clouds or different cluster have a different cost based on the instance type, and you want to calculate what is the cost when I deploy into certain clusters or certain instance types, or how can I minimize that? Or the LAS, like we saw before, finish time fairness, and finally hierarchical. Hierarchical is the multi-object way. And the argument is how, for all of these different objectives, how do I make it heterogeneity aware when I do the schedule? So let's see. How it does is using a matrix. So the representation of the schedule or of the allocation is represented by a matrix called X. And the X will basically contains the GPU type, V100, the P100 or K80, and then each job in the row. So this would mean job 0 should be running on first GPU for 60% of the time and running on the second GPU for 40% of the time until complete. And job 1 is spread out to three different GPU types, and the job 2 is on 20% of the time on V100 and 80% of the K80. So each job, this is the graph representation of this percentage of this allocation. So it means that we're going to switch we're going to suspend the job when it's running one resource and then reallocate to another resource. And if this allocation is represented by the matrix, then based on the optimization goal or objective, then we can come up with the optimal allocation matrix X. And one of the goal objective is the effective throughput. And the throughput is, again, you have to consider the throughput on different devices. So you have the allocation X, you need to multiply for each type of the GPU device. And then you come up, and for this T, the raw throughput on each GPU device is another matrix that you have. Job 0 is throughput is 40 on one GPU and 10 in another GPU and so on. So when you multiply this each element, then you have the throughput of job M based on this allocation X. And now you can optimize for that throughput. The least attended services maximum fairness policy that's basically calculating this. For all the X allocation that I have, I want to maximize the mean, the smallest value of the X throughput of the allocation, and it argues that since the throughut on different devices is different, so previously the throughput is considered the same on each device, right? So, but now since the throughput on each device is different, so you need a normalization factor for the job M, because the throughput of different job on different devices is different. And then you will rewrite this maximum X into a new objective with max mean the throughput over the normalization factor for that individual job. Okay, so this paper's argument is given that matrix and given that normalization, I can put all these policies I can transfer all these policies to be heterogeneous hardware aware because they are calculating a matrix now. And how do we perform the optimization? Objective in terms of the throughput is unchanged. So basically, the optimization algorithm is unchanged because we're just changing how do we calculate the throughput, but the objective of the throughput is actually unchanged for each job. But there's more problem, or there's more questions, more details. Like, let's see, optimization problem has generated an optimal allocation plan X as the job 1 should be running 100% on one device and 50% on two different devices. But how do I map that into the actual assignment of the jobs into the cluster? So they give an example based on the priority score. So if this is the actual optimal placement that we know X job 0 should span 60% for 40% on two different devices. And then this is the run. So every execution is, again, similar to Gandiva's time sharing. It's I'm dividing the time into runs. And each run, I will calculate how many runs that this job has been running in the cluster. Job 0 has been run 3 times on V100, but only 1 run in P100. So 0.2. So if you divide, that's a divide, right? So if you divide this fraction to this run received, you have the priority. So for this current run is 310. And then we calculate the priority as 0.2, 0.40. And for job 1 is this, because it never received any runtime on K80. For now, it's supposed to receive a 0.2% of the K80 resource. So the priority becomes infinitely large. So it's in the next run, it will pick job 0 to be run on the highest priority 0.4 to be run on this P100. And pick job 1 to be run on the K80, and pick job 2 to be run on the V100. Because for each for each type of the device, it gives the highest priority job on that device, and then it depicts that job to that device as the next round it's supposed to be running in the cluster. So they do some evaluation trying to answer some basic questions. Let's see what's interesting here. So if you look at the average GCT as one of the goal, if you use, since their cluster apparently have different number of GPUs, and they use particularly this OGPU V, and the good GPU V100, there's 8 of them, but then majority of them is K80, the old GPU, a slower GPU. And then when they do the LAS, this is the performance, given the different job input rates. So every hour, how many 4 or 6 jobs comes in, 6 new jobs comes in for every hour. And you can see after when you increase the job incoming rate into some threshold, which means now you are oversubscribed to the cluster. You have a job that's not satisfiable in the current cluster, so you have to, put some jobs into the waiting queue. Then, if you use LAS, the average job completion time is pretty high. But if you use the Gavel, it's actually low at 25 hours because it switched the jobs between different GPUs during runtime. And it also has a shorter CDF tail, which means the resource is actually more utilized. You don't have the job waiting in the queue for hundreds of hours for the training. And then for multi-objective, they did the simulation, which is okay. So 0 for 2K. Oh, this is overhead of this scheduler, because you have to calculate the matrix of every job in the cluster that is being running. So they try to show that, okay, for even 2,000 of the jobs, the calculation time of the optimal allocation is less than a second. This is for LAS, 64 seconds. For this is LAS as the single goal, or if you have a hierarchical goal for multiple objectives, and then you basically increase the complexity of the computation, and then it takes a minute to finish those jobs, to actually allocate those 2,000 jobs. And okay, so this slide actually is supposed to be in the middle. I may have misplaced it. So this is one of the previous attacks on the LAS scheduler. It's saying that when you calculate the attended service by number of GPU multiply execution time, this 2 placements, the first placement, I placed the job into 2 servers over 4 GPU, is actually have equivalent service time as the placement of the single job over 4 GPU on the single server. So there's no difference between them, but the second case has optimal performance over the first case because of the network overhead between the 2 servers. And that may actually harm the fairness. That's when I have a private cluster, if I deploy my job to my private cluster, my job actually finishes within this time, within the completion time will be smaller. But since I'm sharing and my job has been stretched out to multiple servers or multiple racks, the completion time is longer to achieve the same training goal. So that becomes the unfairness aspect of the goal. But there are 2 other papers that's also in the recent 2 years, OSDI and SDI talks about the fairness problem and how they attack them. I didn't include any of that, but if you're interested, one of them is called HiveD. The other one is basically this slide, the famous. Let's see. 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 Let's yeah, this where this slice comes from comes as series schedule. So I think I will stop here.